We're very happy to have Carolina Benedetti today talking about quotients of positroids and lattice path matroids.
Okay, thank you very much to the organizers and all of you for being connected. Yeah, so I want to tell you about a project I'm currently working on with Koliak Nauer. And so because of time, I'm gonna be like very rough on the definitions and stuff. But because we start, I just have a small invitation for all of us to self-educate about racism and its impact in academia. Okay, so I'm gonna talk about linear matrix and its relation to the Grassmannian. Then I'll introduce positroids and lattice path matrix. And then I'll present you what problems those are that I'm interested in and working currently with Colia and some of our results. Okay, so the real Grassmannian, so which I'm going to denote by GRKN. So this consists of k-dimensional vector spaces in Rn, and each one of these k-dimensional vector spaces can be represented as a full rank matrix if you fix a basis for your vector space. So for instance, if you have the subspace spanned by these two vectors in R4, then you can just think of this vector space as this rank 2 by 4 matrix. I'm not going to give any of the definitions of the general definitions of what a matrix is. But for the purpose of this talk, it suffices for us to talk about linear matrices. So linear matrices are precisely, let's say, the combinatorial gadget derived from the abstraction of the concept of linear independence or objects in the Grassmannian. So more precisely, if you have an object like the one we have above, an element in the Grassmannian 2,4 or Kn in general, this element of the Grassmannian is going to give rise to what I'm going to call a linear matrix. And for me, a matrix in general and a linear matrix in particular is just going to be a pair. A pair consisting of a ground set, a finite set 1 up to n, which I denote by bracket n, and a collection of subsets. And in this case, our linear matrix, that collection of subsets is going to be given by, from the column space, what subsets of the columns are a basis for the matrix you have at hand. So for instance, with the vector space above, sorry? Was that an echo? Okay, anyway, so from the matrix we have above, the ground set is going to be the set 1 up to 4 because I have 4 columns, and my collection script B is going to be pairs of columns, because this is a rank 2 matrix, pairs of columns whose determinant is non-zero, or whose determinant or the corresponding Plucker coordinate is non-zero. So in this case, those pairs of columns that are non-zero, whose determinant is non-zero, is the column 1, 2, whose determinant is 2, the column 1, 4, and the column 2, 4. Those are the only ones whose determinant is different from 0. And that gives rise to this matrix. If you have not seen what matrices are before, so suffices for you to think of vector spaces as we are doing here today. But this is like an object that I encourage you to learn about. Okay, so as I said, we're going to care only about linear matrices. And positroids are a subset of this linear matrix. So Posnikov, one of the pioneers on the study of positroids, defined it as follows. So we already know what the Grassmannian is. And in the Grassmannian, we're going to consider the subset GR bigger than or equal to 0 that I'm calling the totally non-negative Grassmannian. And this subset is going to consist of those rank K, full rank K matrices whose determinants are all non-negative. So before we only really looked at whether determinants were 0 or not to define a matrix, but here we care about the sign. And positroids are those matrices that can be represented by matrices with this condition, that all the maximal minors or Plucker coordinates or maximal determinants are non-negative. So for instance, here I have a matrix, and this matrix is a matrix on the ground set 1 up to 5, and the collection of bases, I'm declaring it to be these 6 subsets of size 2. So as a matrix, this should correspond to a 2 by 5 matrix. And for this matrix to be a positroid, I should be able to find a matrix, a 2 by 5 matrix, such that the maximal minors that are strictly bigger than 0 correspond precisely to those labeled by the columns 1, 3, 1, 4, 1, 5, and so on. So you can check that this matrix satisfies this. So not all linear matrices are positroids. So in this example, you can yourself go ahead and realize that the matrix on the ground set 4 with this set of bases, although you can find a matrix that represents it, doesn't matter how hard you try, you cannot find it. You cannot find a non-negative matrix that makes of this a positroid. And one of the things about positroids is that they strongly care about the labeling of your ground set. And also because you are computing determinants, and determinants care about the order. So for instance, if you take this matrix is a positroid. You can check that it can be realized by this matrix. And if you compare the matrix M in the second bullet with this one, they are basically the same in the sense that one is a relabeling of the other. So one is not a positroid, but the other one is. So that I just want to point it out. Okay. And one of the nice things about positroids, and in fact, one of the things that really got me into them, is all the combinatorics that is behind them, which I don't really have time to define. But you can encode a positroid by what is known as a Grassmann necklace. And the idea of a Grassmann necklace is that it has enough information for you to recover the whole positroid. So this positroid that you have here can be encoded by this tuple of 2-element subsets. In the sense that if I give you this sequence of 2-element subsets, I can tell you what are all the bases without you having given them to me. And also you can encode your positroid by what is known as a decorated permutation. And these are permutations on 5 elements. In this example, the permutation has is a permutation on the set 1 up to 5, because my positroid is a positroid on 5 elements. And the decoration part comes from the fact that when my permutation has a fixed point, that fixed point is colored with an underline or an overline. If you're familiar with the language of matrix, underline means you have a loop, overline means you have a co-loop. And in this case, 2 is a loop because it does not show up on any basis. And there are way more combinatorial objects that allows you to think of positroids. Okay, so I also need to define what a lattice path matrix is. And let me show you a picture that is, I guess, easier to describe them. So for a lattice path matrix, so if you want to describe what a lattice path matrix on the ground set N of rank K is, you just need to present what are the K tuples that are bases of your matrix. And graphically, you can do it as follows. So for your lattice path matrix to be fully described, you only need to tell me what I'm going to call the upper path and the lower path. So this upper path is a path that allows you to go, if you want, from the origin or from the southwest corner to the northeast corner in a grid of size K by n minus K. So in this case, my grid has 6 rows and n minus K columns. And my upper path I draw here. So the upper path just tells me these are the sequence of north steps I take to go from southwest to northeast. And the lower path tells me the same. And the basis of my lattice path matrix will be all the things that I can draw in between. So for instance, if I consider this subset of size 6, this subset of size 6 corresponds precisely to the north steps of this red path that I have drawn here. And any basis of this lattice path matrix arises this way, okay? Okay, and so why do I care about lattice path matrix? Because they are positroids. So not only they are linear matrices, but they are also positroids. So you can realize them as matrices whose maximum minors are non-negative. Okay, so I need one more piece of information before presenting you the problems I'm interested in. And so since we already know about the Grassmannian and its relation to linear matrix, so the flag variety, which you can think of a point in the full flag variety in Rn as a sequence of n vector spaces, one inside the other, and each one of different rank. So in a similar fashion as you can think of points in the Grassmannian as full rank matrices, k by n matrices, here you can also think of points in the full flag variety as full rank n by n matrices. So for instance, these 3 by 3 matrix here in the end, or these sequences of matrices are a point in the full flag variety, but really all the information is condensed in the last matrix. The last matrix is a 3 by 3 full rank matrix. And the first I rows tells you precisely what is the I-dimensional vector space that composes your point in the flag variety. And in the same way that matrices are a generalization of the concept of linear space, quotients of matrices are a generalization of, let's say, points in the full flag variety. So I guess I can say a couple of words about it. So there are lots of ways of defining what a quotient of matrix is, just as there are lots of ways of defining what a matrix is. So in this setting, you can think of my definition as follows. So since the matrix that we are considering are linear, you can think of what are the minimally dependent sets of columns. So for instance, the first matrix, if you look at its sets of columns, column 1 is linearly dependent, column 3 is linearly dependent. And although columns 1 and 2 are linearly dependent, they are not minimal because there is a smaller column containing them that is linearly dependent. So circuits are going to be like the counterpart of bases in the sense that bases are maximally linearly independent and circuits are minimal linearly dependent subsets of the column set. And so what happens is that with this in mind, you can find a quotient of matrix. So you can say that two matrices M and N, or if you have a matrix M and a matrix N, both on the same ground set, we can say that M is a quotient of N if the circuits of N are unions of circuits of M. So for instance, in this example, the matrix M2 has as circuits only the subset 1, 3. So only the subset 1, 3 is the only minimally linearly dependent set of columns. And the circuits of the first one, as we said, are the sets 1 and the set 3. And being M1 a quotient of M2 can be verified because the only circuit of M2, which is 1, 3, is a union of the circuits of the small one, which are 1 and 3. So you can do this with two matrices, and in fact, you can do it for a collection of matrices. So a collection of n matrices on the same ground set n are a full flag matrix if Mi is a quotient of Mi plus 1. And basically, again, this notion is well captured in points of the flag variety. So again, there is a nice parallel or interplay between geometry and matrix. So points in the Grassmannian are linear matrices. If you know a little bit about Grassmannians. So lattice path matrices represent generic points in Richardson cells. Positroids correspond to points in the totally non-negative Grassmannian. Representable flag matrices give us, or can be thought of as points in the flag variety. And now the first question is, what can we say about the non-negative flag variety? Just in the same way that we ask ourselves, what can we say about the totally non-negative Grassmannian? So you can think of the totally non-negative flag variety as n by n matrices, full rank n by n matrices, such that the top I rows are a positroid. So are a point in the totally non-negative Grassmannian IN. And the question is, how do we fill this gap? So what's going to be the matroidal gadget that allows us to think of points in the totally non-negative flag variety? So in view of this, so here are 3 problems that are related to this. So one of these problems is, if you have 2 positroids, can you make use of their combinatorics to tell whether these 2 positroids are a quotient of one another? If you take it, say, a step higher, can we actually fill this blank by simply saying that every point in the non-negative flag variety corresponds just to a flag of positroids? And the third question is, since lattice path matrices are positroids, take a flag of lattice path matrix. What can we say of the collection of flags of lattice path matrix? So these are like the 3 questions. And the first one, we work on that partially having or obtain partial results with Anastasia Chavez and Daniel Tamayo. We studied those positroids that are quotient of uniform matrix. Uniform matrices are positroids. So basically the idea is that this poset you see here is the poset on all the decorated permutations on 3 elements. Each one of them corresponds bijectively to all the positroids of on a set of size 3. So this is ranked by ranked. So in this row, in the first row, we have all the positroids of rank 1 and 3, in the second row, the positroids of rank 2, and so on. And the ones that are highlighted in red are the uniform matrices. And so what we studied was who are these uniform matrices covering in this poset. And the relation here is P is a quotient of Q. And again, this was done by only uniform matrices. So with Collier, we wanted to understand this better, perhaps for a bigger family. And so far, we have managed to characterize completely full flags of lattice path matrix. So if you hand me a lattice path matrix, I can tell you what are the lattice path matrices that are quotient of that one. So I can illustrate this with this diagram here. So in the right-hand side, you have a lattice path matrix on n elements of rank K. And for you to construct all the possible quotients derived from it, the quotients of rank K minus 1, so you do the following. You are gonna take a north step. So one of the north steps here I labeled by UJ. And to construct a quotient, you're just going to pick a lower step, and that lower step has to be weakly to the right of that upper step you selected. And with your choice, you delete both of them. You delete UJ and LI, and that gives you the lattice path matrix on the left, and that happens to be a quotient of the one on the right. And that's an if and only if. So going back to question 2, so we understand quotients of lattice path matrix, but still we want to know if any flag, full flag of positroids corresponds to points in the non-negative flag variety. So in the, say, in the context of this poset, what that would mean is every saturated chain, is every maximal chain in this poset a point in the non-negative flag variety. So can we represent each one of these chains with a 3x3 matrix such that the top I rows have this non-negative condition? And surprisingly, at least to me, the answer is no. So for instance, if you take the flag 3, 2, 1, 2, 1, 3, I'm omitting the bottom and the top because really they are not relevant. So this flag, at least this flag, cannot be represented by a point in the non-negative flag variety. So I can tell you afterwards, or you can check it by yourself. So
You've got
the
about
answer
5
is
minutes
no.
left, Carolina.
Okay, yeah, I'm almost done. So the answer is no, but since we already have a better handle on lattice path or of quotients of lattice path matrix, what can we say about them? So there is this very nice result of Lauren Williams and Zuckerman, and that basically tells you that you can think of these points in the non-negative flag variety as, okay, they are a flag matrix, moreover, they are a flag positroid. But if you think of this flag matrix as its matrix polytope, flag matrix polytope, this flag matrix polytope is actually an interval in the strong Bruja order. So what that means is that, so here in the right, we have the Bruja order of on 3 elements, and each interval in the Bruja graph corresponds to a flag of positroids. So at least by counting in this case, on the left-hand side, you have 22 chains, 22 maximal chains. On the right-hand side, you have 19 intervals. So that already assures us that not every flag of positroids is an interval, is a point in the non-negative Grassmannian. And in fact, out of those intervals out of those points in the non-negative flag variety, only 17 of them, not all of them, happen to be flags of lattice path matrix. So finally, so what can still we say about, or what else can we say about flags of lattice path matrix as points in the non-negative flag variety? So far we know that flags of lattice path matrix are indeed intervals in the Bruja order, which is pretty good. And we don't know how to give a full characterization of intervals in the Bruja order that correspond to flags of lattice path matrix, but we have some partial results in that sense. So at least some faces of the right permutahedra we can identify with flags of lattice path matrix, and moreover, hypercubes in the weak Bruja order also can be thought of as certain flags of lattice path matrix. I guess this is a good point to stop, and so that's it. Thank you very much.
Thank you.
Are there any questions? There were a couple of questions on the chat. One was about more representations. I think is when you talk about the matrix at the beginning.
Sorry, can you repeat that?
There was a question on the chat, like at 10 minutes once you started, asking if there were more representations.
More representations? What do you? So who's asking the question?
I'll ask. Okay.
Yeah.
Can you go back to page 6?
Page 6. Okay. Hold on. Here?
Yeah. You have a matrix representation here, right?
Yeah.
Sometimes you have, sometimes you don't. But if you have, you can have multiple representation of, right?
Yeah. And I mean, it's difficult to be able to find such a matrix representation. So like if we want to check that something is a positroid, perhaps finding a matrix representation is not the best way.
Thank
you. Okay, so there was another question saying Art Duval asking if there was a purple 9 that should be a 10. I assume that is on the slide where you...
The lattice path matroid diagram.
Yeah.
I was trying really quickly to figure out what was going on.
So which one? So
when you had the U and the L, that one. Yeah, I couldn't. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Oh, the 9 is for the up going, not the. Never mind. I think I got it.
Right. Yeah, this encodes the north steps. Yeah.
Okay. Sorry. Thank you.
And Derek is asking if there is any hidden code in the last slide.
At least not on purpose. It's just a way of labeling one of the intervals. So every permutation can be thought of as a full flag of lattice path matrix, and then in this picture, each edge is also labeled by a full flag of lattice path matrix that maybe you can see the relation with the vertices it is adjacent to, and also the maximal phase. But no, I should have done a secret message or something.
Yeah, actually, there is an AlCoVE over there. Just have to be creative and figure out where. Any other question? The chat is a little bit delayed, so if you have a question, just unmute yourself and go ahead. And now we have this awkward minute of waiting for someone. If you turn it away, look in the video.
Yeah, that's it. Thank you, Nathan. That's precisely it.
Okay, so let's thanks Carolina again.
Thank you.
For the really nice talk. Thank you.